Okay, so our first three homework assignments that we went over for this particular unit all dealt with drawing Lewis structures for compounds, mostly covalent compounds. Once we've mastered that, now in our last lecture, we learned that if you can draw the Lewis structure for a compound, you can then also use the Lewis structure in conjunction with the valence shell electron pair repulsion theory, Vsepr, to predict shapes of molecules. And we'll be doing some of that from Monday's homework. We're going to learn one more thing now that you can glean from a Lewis structure. Besides predicting the shape of the molecule with the Vsepr theory, today we're going to learn how to predict molecular polarity, which means whether a molecule is polar or not. Now, we've heard the word polarity before, back in the beginning of this unit. When two atoms share electrons, there's a couple different ways they can share those electrons. If they share the electrons evenly, we call that a nonpolar bond. But if they share the electrons unevenly, then whichever atom is hogging the electrons, the negative charge is next to them more often, and the other atom is losing the electrons, so they're going to be more positively charged. That bond will therefore have a positive end and a negative end, and thus it's called a polar molecule. So a bond is considered polar if the bond has a positive end and a negative end, and this is due to one of the atoms having a greater attraction for the shared electrons, so it pulls the shared electrons towards it, and it becomes negative, and then while that happens, the other side of the bond becomes positive. Now, how do you predict if a bond is a polar bond like this? Well, you have to use this tool, this number that was derived by Linus Pauling called electronegativities. An electronegativity is a numerical value that tells you how much an atom attracts shared electrons. The higher the electronegativity, the more the atom pulls shared electrons towards it, the more likely it's going to be the negative end of a polar bond. We're not going to learn today how to tell if a bond is polar or not. We actually already did that. It's by electronegativities. The higher the electronegativity, then if two atoms are bonding together with different electronegativities, that means one atom likes electrons more than the other, the bond will be polar. We're going to talk about whether molecules are polar or not. So if we talk about molecules, molecules are considered polar if they have a positive end to them and a negative end. And so we're going to go through a couple of techniques to learn how to predict if a molecule is polar or not. If you took Chem 3, you've probably dealt with this before. There's a simple and very visual way to predict if a molecule is polar or not. We're going to go through this first because it's actually very satisfying, and I think you can really see the concept well, but it unfortunately doesn't work all the time. So after we've got this down with a few examples, we're going to go to the more exact technique for predicting whether molecules are polar or not, and we'll see if we can learn that today. So if you want to be able to determine if a molecule is polar or not, I'm going to give you 5 steps to follow. And we've done several of these already. First step is you're going to have to draw the correct Lewis structure. So that's why we've had homework on lectures 2A, 2B, and 2C, because we want you to be able to draw the correct Lewis structure for a covalently bonded molecule. Now, in our last lecture, 2D, we learned how to use the Vsepr theory to predict the shape of the molecule. And so that's going to be needed here. You're going to have to predict the shape of the molecule with the Vsepr theory, and then you're going to have to use your expertise in your artistic ability and try to draw its correct shape to the best of your ability as you can. Once you've drawn the molecule in the correct shape, then we're going to start analyzing every single bond in the molecule, and we're going to have to answer whether the bonds in the molecule are polar or nonpolar. How do we do that? We use electronegativities. So you're going to use electronegativities to determine if the bonds in a molecule are polar or nonpolar. And this is determined by just taking the electronegativities of the two atoms that are bonding and subtracting them. If you subtract the electronegativities and the answer comes out 0, that means they have equal attraction for the shared electrons, and that would be a nonpolar bond. But if the atoms have different electronegativities, when you subtract them, you're going to get a number bigger than 0. That means the bond will be polar. And if you determine a bond is polar, what we need to do on our picture is label the positive ends and the negative ends of every single bond. So for any polar bond that you deduce in your molecule, you're going to label the positive end and the negative end with a delta positive and a delta negative sign. We could simply just put a positive sign and a negative sign, but to a chemist, that actually means a positive 1 charge and a negative 1 charge. And the uneven sharing of electrons only creates a slightly negative charge and a slightly positive charge. So the lower case Greek letter delta actually just means partially. So partially positive, partially negative. Once you've done this, you're going to have a geometrically correct picture of the molecule with every atom labeled as either positive or negative in it. And then when you look at it, you have to ask yourself, wow, are all the positives on one side of the molecule and all the negatives on the other? You'd be able to tell that if you could draw a line through the molecule that separates all the positives from all the negatives. And if you can draw that line that separates all the positives from all the negatives, that means the molecule will be polar. And that's how we determine if molecules are polar. If you cannot draw a line that separates all the positives from the negatives, then the molecule must be nonpolar. So we're going to start with an example. We're going to do water. And as I said a few days ago, if I say water, I want you to know the formula is H2O. The Lewis structure for this will be determined by first counting up the total number of valence electrons for 2 hydrogens and an oxygen. 1 and 1 and 6 would add up to 8. The skeletal structure puts oxygen in the central position and bonds the 2 hydrogens to it. And then the remaining electrons are added as lone pairs. And so when you do that, you wind up getting a Lewis structure that would look like this. The oxygen makes single bonds with the 2 hydrogens, and the oxygen atom has 2 lone pairs in its outer shell. This Lewis structure does not tell you the shape of the molecule. It only tells you that H is bonded to O, bonded to H, and they're bonded with single bonds. The shape of the molecule comes from applying Vsepr theory. And that means focusing in on the central atom, which is the oxygen, and determining something about the oxygen that's called its steric number. That's how many atoms are bonded to it and how many lone pairs it has, because that number is going to be the number of negatively charged repelling groups that are going to try to spread themselves out as far apart as possible around the O. So if you look at the oxygen, it has 2 hydrogens bonded to it, and it has 2 lone pairs. 2 plus 2 is 4. Oxygen has a steric number of 4. And as we discussed yesterday, if you can visualize how could you spread 4 groups as far apart as possible around a central atom, 4 groups always spread out most efficiently as a tetrahedron. So the 2 lone pairs and the 2 hydrogens would spread out onto the 4 corners of a tetrahedron. We would say the orbital geometry of water is tetrahedral, but that's not the molecular geometry. The molecular geometry only defines where the atoms are. So in our tetrahedral geometry, you would actually have a lone pair pointing up and another lone pair pointing out to the right. But if I erase those, then what's left over are only the atoms, and that dictates or determines the shape of the molecule. That's a bent shape. The angle of the water molecule is the tetrahedral angle of 109.5 theoretically. So what we've done is we've drawn the Lewis structure, and then we've drawn the proper shape of a water molecule. This is kind of a fancy way to draw a bent shape. If that's too fancy for you, you can just draw the O and the H's all flat on the paper, but just make sure the angle between the H's is 109.5. Once you have the shape drawn correctly, now we have to determine if the bonds are polar or not. And this is where you're going to have to look up the electronegativities for oxygen and hydrogen. They're found on our class website on handout 8. And if you look those up, oxygen's electronegativity is 3.5, hydrogen's is 2.1. It's the difference between these you want to know. If the difference is 0, that means they share electrons evenly, the bond is nonpolar. But this clearly is not 0, this difference is 1.4. So as long as the difference is greater than 0, these are polar bonds. And in fact, the bigger the difference, the more polar they are. And in fact, if the difference just got a little bit bigger, all the way up to 1.7, it would be so polar that the electrons would be transferred and you would actually have ionic bonds in that case. But we didn't quite reach that threshold. So this 1.4 difference just means unequal sharing of the bonds, shared electrons. So therefore, it's a polar bond. So now what you have to do is you have to go to the picture you've drawn on the left, and we're going to label each of the 2 bonds in the water molecule with a delta positive and a delta negative on their negative and positive ends respectively. Now, if you look at this bond right here, how do I know which end is going to be positive and which end is going to be negative? You have to know the definition of electronegativity. What did Pauling say electronegativity was? It's the attraction of an atom for shared electrons. And the higher the number, the more that atom attracts shared electrons. So if you look at the 2 numbers, which one attracts shared electrons more? It's got to be this one. If this attracts shared electrons more and the electrons go towards the oxygen end of the bond is going to be negative. So we're going to label each bond with the delta positive and the delta negative. So the oxygen gets the delta negative because it has the higher electronegativity. The H is the delta positive because it's the lower electronegativity. And I'm going to do the exact same thing for the other bond. The O end is going to be negative and the H end is going to be positive. So when you put your delta positives and delta negatives on every single bond in the molecule, now you stand back and you look at it and you go, are all the negatives on one side and all the positives on the other? And you can verify that by drawing a line on your paper that separates all the positives from all the negatives. Look at that. This means the molecule has a negative end, which is the upper right, and a positive end, which is the lower left. Therefore, this is a polar molecule. So in this analysis, very pictorial, if you can draw the correct shape, label every atom as positive or negative, and then if you can draw a line separating all the positives from all the negatives, that proves the molecule's polar. The oxygen end of a water molecule is negative. The hydrogen end of a water molecule is positive. Any questions on what we've done up to this point? Okay, let's try a couple more examples. If I were to ask you to draw the Lewis structure for ammonia, I would expect you to know the formula of that simple molecule. It's NH3, total of 8 valence electrons. Skeletal structure would put 3 bonds between nitrogens and hydrogens, and the final 2 electrons would go in the outer shell of the nitrogen to give it an octet. In this particular structure, if we want to now predict whether it's polar or not, you are going to first determine the steric number of the nitrogen, and from that we're going to predict what the shape of the molecule is. Let's see, Mr. Gomez is asking if bonds are polar, but you cannot draw a line separating between the charges. Is the molecule nonpolar? And Mr. Gomez, you're about 5 minutes ahead of pace, but the answer to your question is yes, and you'll see that momentarily. So for the ammonia molecule, because it has 3 bonded atoms and 1 lone pair, that's a steric number of 4. These 4 groups would spread themselves out as a tetrahedron. We would say the orbital geometry of ammonia is a tetrahedral geometry, but the molecular geometry is just defined by where the atoms are. So the atoms are located in what we call a trigonal planar, a trigonal pyramidal shape. I'm essentially drawing a tetrahedron. I'm just leaving the lone pair off, which would be pointing straight up. If you leave that off, the remaining atoms make a little pyramid where the hydrogens are the base, a triangular base, and they're all coming up to the nitrogen at the top. So that's our most accurate drawing we can make of the actual geometry of the molecule. Once you have the geometry that's correctly drawn, and you determine if the bonds themselves are polar or not, handout 8 or the text, or I guess anywhere on the internet, the electronegativities of nitrogen. If they're the same, the bonds are nonpolar. You wouldn't put any delta positives or delta negatives. But if the electronegativities are different, that means you have a difference in attraction for the shared electrons, and one atom is going to be hogging the electrons from the other. The one that hogs the electrons is going to be the one with a higher electronegativity. So nitrogen, which has a higher electronegativity, pulls the electrons from the hydrogen. So in all 3 of these bonds, the nitrogen end is going to be negative, be positive. Label this bond. The next bond, label hydrogen positive, nitrogen negative. And the final bond, label hydrogen positive and nitrogen negative. Okay? You will not need to memorize any electronegativity values. So if I want you to have them, I will give them to you. But there'll be some instances where you will not actually need to know electronegativities, but you'll need to be able to predict whether one atom is higher than another. And we get to that point in the lecture today, I'll sort of point out when I would expect you to do something like that. So memorizing them, absolutely not necessary. So now that we have all the positives and negatives written on our molecule, can you draw a line that separates all the positives from all the negatives? It's a little bit harder to see, but you absolutely can. That line would go right here. The very top of the pyramid, the nitrogen, is the negative end of the molecule, and the base of the pyramid, the hydrogens, is the positive end. So because all the positives and negatives can be separated from each other, we would say this is a polar molecule. Okay? So Mr. Gomez asks, how come there's 3 negatives next to the nitrogen? And that's because what I did is I labeled each bond individually. So Mr. Gomez, I labeled this bond first, then I labeled the second bond, then I labeled the third bond. You have to label every single bond. Now, if you want to just draw one big giant negative next to the nitrogen, that's fine. But I thought if I did it this way, you could see I'm actually doing 3 analyses of each of the 3 bonds. Okay? And then let's see. Nitrogen has only 2 lone pairs. Actually, nitrogen does not have 2 lone pairs. It has 1 lone pair. But when you draw the shape of the molecule, we usually lone pair off, so I didn't put it there. I showed where the atoms were. You could put the lone pair up here, but that's not used in an analysis to determine whether the molecule is polar or not. Okay? So because we can draw this line that separates all the positives from the negatives, that means the ammonia molecule must be polar. The nitrogen end is negative, the hydrogen end is positive. Okay? Now, in terms of a question that was brought up by, I think Mr. Gomez did, let's look at the molecule carbon tetrafluoride. What would be the formula for carbon tetrafluoride?
CF4.
CF4.
Perfect. That could be one of the nomenclature questions you have on your nomenclature quiz next week. So don't forget, when you come back to lab, your first day in lab, at the beginning of your lab period, we'll take our nomenclature quiz where I'll ask you to give me the names or formulas of 20 different compounds, and this certainly could be one of them. For CF4, if you draw the Lewis structure, there's a total of 32 valence electrons. If we draw the skeletal structure with carbon bonded to 4 fluorines, then the rest of the electrons filled in as lone pairs, it works out that 32 electrons perfectly allows every single atom to have an octet configuration. So this would be your Lewis structure for carbon tetrafluoride. If I ask you, is it a polar molecule or not, you first have to determine the shape. The steric number of the carbon is 4, so those 4 fluorines will spread themselves out as a tetrahedron. And now I don't have any lone pairs to ignore, so I'm actually going to draw all the fluorines there. And now we actually have the shape of the molecule drawn correctly. And if you remember from yesterday, you're drawing a tetrahedron. You draw one atom bonded straight up on the plane of the paper, the other going down to the right on the plane of the paper with an angle slightly bigger than 90 degrees, because that angle is 109.5. Then the other 2 fluorines, one of them comes out towards you, one of them goes behind the plane of the paper itself. So you draw a wedge to show the fluorine is coming out to the left, and a dotted line to show the fluorine is going behind the paper, also to the left. Now, if we want to predict whether it's polar or not, the next step is to determine whether the bonds are polar. We have to look up the electronegativities of carbon and fluorine. Carbon is 2.5, fluorine is 4.0. The difference is greater than 0, it's 1.5. So that means the bonds are polar. And in each bond, the fluorine, which has the higher electronegativity, is going to be the negative end, and the carbon, which has the lower electronegativity, will be the positive end. So I'm going to label every single bond one at a time. Here we go. Negative fluorine, positive carbon. Negative fluorine, positive carbon. Negative fluorine, positive carbon. Negative fluorine, positive carbon, and now every single one is labeled. Okay? Mr. DiFilippo, I think, asked, is electronegativity is always positive? Yes. And their difference, you always just take the absolute value and go biggest one minus smallest one. So it'll always be a positive value. Yeah.
Thank you.
Now, take a look at this molecule here. Can you draw a line that separates all the positives from all the negatives?
No.
Can't do it. So this molecule has polar bonds, but unfortunately, the molecule itself doesn't have a positive end or a negative end. So all of the positives cannot be separated from all the negatives. So therefore, the CF4 molecule is nonpolar.
If you were to draw a line, the charges would cancel out. So is that another way to check if it's nonpolar?
Charges always cancel out, so that doesn't tell you anything. It really depends upon whether the charges are symmetrical or asymmetrical in the molecule. In like water, the charges were asymmetrical. The negatives were on one side, the positives were on the other. It was polar. In this case, the negatives are perfectly symmetrical all the way around. And so therefore, it does not have a positive end and a negative end. Does that make sense?
Yes, thank you.
Now, what'll get you on the test, and let me show you this, watch this, is what people will do. Okay, there's the molecule. Is the molecule polar or not? Let me draw the shape. Let me look up the electronegativities. Oh, fluorine has a higher electronegativity. That means it's polar, and they'll write the molecule is polar because they're not clear on the difference between molecule and bonds. This only tells you the bonds are polar. It doesn't mean the molecule is polar necessarily, because as we saw, curses, you can't draw a line separating the positives from the negatives. So even though the bonds are polar, the molecule is nonpolar. The molecule does not have a positive end and a negative end, okay? So how do you know which, now you said which molecule is positive or negative. You really mean which atom in each bond is positive or negative. It has to do with the electronegativities. What does electronegativity mean? It means the attraction of an atom for shared electrons. So the atom that has the higher electronegativity attracts electrons more. Look on this page. Which atom attracts electrons more, carbon or fluorine? So that means the electrons get pulled to the fluorine, so the fluorine is the negative end. The moral of the story is it's always the atom with the higher electronegativity. Okay, is that good? Good, excellent, okay. So that's a lovely technique, but unfortunately it doesn't always work. It's so, I find, satisfying. You can see the positive half and the negative half. Who wouldn't love that? But there are instances where it doesn't work, so we have to learn a more exact way to determine if molecules are polar or nonpolar. And this more exact way uses a concept known as vectors. If you've had physics, you know what a vector is. If you've had some advanced calculus, you know what a vector is. If you haven't, you go, I think it's a disease, but I'm not really sure. But we're going to talk about using vectors in a simplified way that we can actually all get through it, even if you've never heard of them before. So here's the way in which we're going to predict whether a molecule is polar or nonpolar that's slightly different than the lovely visual way you just saw. First three steps are the same. We're going to draw the correct Lewis structure for the molecule. Once you've done that, with the Vsepr theory, you're going to predict its shape, and then you're going to draw its correct shape. Then you're going to look up electronegativities. Unless you're Miss Eckes, she'll memorize them all, but everybody else, you can just look them up. And you're going to use the electronegativities to determine if the bonds in the molecule are polar or nonpolar. And here's where the technique varies now. When we were talking about polar bonds a couple lectures ago, we only did a little bit, so it may not stick really well, but we showed that you could say a bond is polar or nonpolar by putting a delta positive on one side and a delta negative on the other, and we use that in our first technique here. But there's another way to demonstrate that a bond is polar or not, is by putting an arrow along the bond, which is called a dipole moment arrow. And the arrow along the bond points towards the negative end. So what we're going to do is we're going to use dipole moment arrows instead of delta positives and delta negatives. So for any bond that turns out to be polar, we're going to draw a dipole moment arrow pointing to the negative end of the bond from the positive end. These dipole moment arrows are what we call vectors. A vector is something that indicates two things. It indicates direction and magnitude. So it's an arrow. The direction should be pretty clear. It's telling you which way the electrons are being pulled. But what's magnitude? What are we talking about? If you have two atoms that are bonding and their electronegativity difference is 1.0, you would draw the dipole moment arrow at some length that would represent the difference of 1.0 in electronegativities. But if you have two other atoms that are bonding and their electronegativity difference is only 0.5, how big would you draw the arrow? Half as big. So the length of the arrow tells the difference in electronegativities. It tells you how much more one atom is pulling electrons away from the other, because the bigger the difference in electronegativities, the more electrons get pulled. So the length of the arrows you draw are going to be relevant because they need to show magnitude. Now, once we've drawn all these dipole moment arrows in our molecule, what you're going to do is you're going to see, can I cancel out vectors? And this is the one thing about vectors we're going to learn. How can you show vectors canceling out? You'll cancel out as many sets of vectors as you can, and then at the very end, you're going to look and see if there's any dipole moment arrows left over. If the molecule has extra dipole moment arrows left over, it's polar, but if they all cancel out, it's nonpolar. So we're going to cancel out symmetrical dipole moments, and then if any dipole moments remain at the end, the molecule will be considered polar. And we'll do a number of examples of this to try to show you how this works. So before we do any examples on any real molecules, I've got to show you what I mean by symmetrical dipole moments, okay? So let's say we have a molecule that has several different polar bonds in it. Dipole moments that point along those bonds that are of equal magnitude will be symmetrical if, and I'm going to give you 3 conditions that if you're not the master of vectors, if you just learn these 3 conditions, then you're going to be able to handle vectors with no trouble whatsoever. So dipole moments of equal magnitude are symmetrical if there are 2 dipole moments that are arranged linear to each other. Let me give you an example of that. Let's say we have a molecule whose shape looks like this. And let's say these bonds are polar. And let's say element Y has a higher electronegativity than element B. Okay? If that's the case, we now know that the dipole moment arrow would point towards the more electronegative element Y. So I would draw a dipole moment arrow pointing from the X to the Y on the left, and a dipole moment pointing from the X to the Y on the right. Okay? The dipole moment arrow points towards the more negative atom, and then towards the more positive atom. They put a hash mark on there because that looks like a little positive sign. Okay? Those 2 vectors are considered symmetrical. And if you imagine yourself as in the part X, where X is, and the Y's are 2 people grabbing onto your arms on the left and the right, and they're both pulling you equally. If they pull you equally, do you move? You don't, because that's symmetrical. So these 2 dipole moments are tugging on the electrons both to the left and the right equally, and because they're equal magnitude, the X doesn't move. That means the electrons don't move, and so that would be perfectly symmetrical. Now, if you take some physics, what you're going to see is that you can do some mathematics with these vectors, and I'm going to do a little bit of mathematics with the vectors for you today. So let's see if we can do this for you. Here's a y-axis, here's an x-axis, okay? So let's say right at the origin is where our central atom X is, okay? It's located right here, okay? And so we have atom Y here, atom Y here. And these 2 bonds, let's say the electronegativity for X is 2.0 and the electronegativity for Y is 3.0. So the difference in electronegativity equals 1.0. It's going to be for both of those bonds. So what I'm going to do is I'm going to draw a dipole moment arrow of equal magnitude pointing in the 2 different directions, like this. Here's my dipole moment arrow pointing to the left. Here's my dipole arrow pointing to the right. The length has to correspond to the electronegativity difference. So this length would correspond to like 1.0 centimeters. This would correspond to 1.0. But direction is important in physics. And when you're on a number line or an XY coordinate space, if you're going this way, that's positive. If you're going this way, that's negative. So this values vector is written as 1.0. This one is written, it's going in the opposite direction, right? Negative 1.0. What do you get when you add those together? Vector addition means they add up to nothing. That means they cancel out. So the effect of these 2 vectors is that they cancel each other out. And so the electrons are not pulled to the left, the electrons are not pulled to the right. So this is called a symmetrical arrangement. It does not cause a molecule to be polar, it actually causes it to be nonpolar. Okay? So if you ever see 2 vectors that are in a linear array and they're equal in magnitude, they will cancel out because it's like +1 to the left and -1 to the right. Now, if those 2 vectors were not equal in magnitude, let's say the atom Y, one was atom Y on the left, and this was atom Z over here. What if this dipole moment was way bigger than this one? So they were not equal magnitudes, then they don't cancel out, right? So they only cancel out if the magnitudes are equal, all right? So that's one thing you will need to know. The next arrangement you need to understand is that if you have 3 dipole moments that are arranged in a trigonal planar geometry, those will be symmetrical and their dipole moments can add together to make 0, just like we did before. So if you have a molecule that happens to have a trigonal planar shape, and these bonds in this molecule are all polar, just like the last one, and you would draw your dipole moment arrows like this, one pointing up and the other 2 pointing down slightly to the left and the right. Well, I'm telling you, this is a symmetrical arrangement. If you imagine yourself lying on the ground where position X is, and somebody's pulling at the top of you and pulling down at those 2 angles, and they're all pulling evenly, you don't move because it's equal force in those 3 specific directions because it's so symmetrical. If you want to see why it is mathematically, we can do that. Let's see how far back I can go on this. It's just going to take too long. I'm going to erase it all. Let's try it again. So let's have a y-axis and an x-axis, okay? And we have our atoms. Here's the one in the middle, the x. The atom y is here. The other atom y is here. The other atom y is here. So our dipole moments would point like this, and like this. So this dipole moment, this dipole moment, and this dipole moment, and their magnitudes, if I once again assume x has an electronegativity of 2.0, y has an electronegativity of 3.0, then the change in electronegativity, which is going to represent the length of our vector, is going to be 1.0. Okay? So I've told you that if you add up those three vectors, they're going to cancel out and make 0, just like the one did before, where the one pointed to the left and pointed to the right and they canceled out. Can you see that? It's kind of hard to do now. How do we do that in 2 dimensions? Well, what we're going to do is we're going to break these vectors down into something called their x and y components. You see this vector here? When you're dealing with vectors, that's going to be equal to a vector that points directly along the x-axis here. Oh, I made it move, sorry. Move up a little bit. I got to try that again. A vector pointing along the x-axis here like this, and then another vector pointing from the top down. So this is breaking down this vector into its x and y components. So I'm going to look at the green vectors instead of this red one. And I can do the same thing for this other one that's pointing to the left. I can break it down into an x component and into a y component. This one's already directly on the y-axis, so I don't have to break it down into x and y components. It's already set for us. So watch this. We're going to try to figure out the vectors cancel out along the x-axis and if the vectors cancel out along the y-axis. Let's do the y-axis first. You see what this vector is doing? It's pointing 1.0 in the upward direction. Does that make sense? Okay. So you see these two vectors here. These are pointing in the upward direction. Now, do they cancel out with that one? You've got to figure out what this value is. How do we do that? What's this angle here in trigonal planar geometry?
109.5.
No, it's 1/3 of a circle.
Oh.
Right?
Yeah.
So if that's 120 degrees because it's 1/3 of a circle, what's this angle right here?
60
degrees.
Try again.
30.
30, because this is 90, and then 30 more would make 120. Okay? So if this is a 30-degree angle, this part of the triangle is 1.0, because that's the difference in electronegativities. What's going to be my value for x here? How do you figure that out? Who's
120 minus 30.
120 minus 30 is just calculating what this angle is right here. I want to calculate this distance here, this leg, this, I should call it y. It's on the y-axis, y value. How's that related to 30 degrees and 1.0?
Is it SOHCAHTOA?
Say it again.
SOHCAHTOA.
So you have to tell me what that means.
Like the sin or the tangent.
Something. Which one is it? Which one do you want to
Would
use?
it be a cosine
Yeah,
of
30.
See this?
1 times sine 30. 1
Opposite,
times sine 30 equals y.
opposite over hypotenuse is sine. So the sine of angle 30 equals opposite over hypotenuse. So if I bring the 1.0 to the other side, y has to equal 1 multiplied by sine of 30. What's the sine of 30? Right, 0.5, excellent. But see, it's pointing in the downward direction. So that means it's negative 0.5. See this one over here on the other side? I could go through the whole same thing again, but it's exactly the same, negative 0.5. So what does this 1.0 and the negative 0.5 and the negative 0.5 all add up to make?
Fine.
0, right? 1 minus a half is 0. So that means on the y direction, the vectors cancel out because the 1.0 pointing up is canceled out by the two little y components pointing down of negative 0.5 and negative 0.5. Okay? Now, let's figure out on the x direction what the value for these two values of x are right here, because they're the only way the vectors are pointing left and right. How do you get this value of x right here?
Cosine of 30 degrees times 1.
Pythagorean theorem.
Equals adjacent over hypotenuse. So 1.0 times cosine of 30 will equal our x value. Anybody remember what the cosine of 30 is?
1/2.
Close, it's radical 3 over 2. So this vector here is positive radical 3 over 2. This vector is negative radical 3 over 2. What happens when you add those together? 0. So therefore, these three red vectors, when I break them down into their x and y components, we can mathematically prove that they cancel out in the x direction, they cancel out in the y direction, they all add up to 0. That's what I mean when I say vectors are symmetrical and they cancel out. So whenever you have a situation like this, where you have three vectors pointing at the three corners of a trigonal planar geometry, they are perfectly symmetrical, they will all cancel out. And that's the second symmetrical arrangement I need you to know. Linear cancel out, trigonal planar cancel out. Let's give you one more. If you have a molecule that has 4 dipole moments that are equal in magnitude, and they're arranged in a tetrahedron, so here's a tetrahedral molecule, these are symmetrical also. So if these are all polar bonds and I draw the 4 dipole moment arrows here, they will all cancel out. I am not going to go through the analysis with this for you because this requires the x, y, and z axes. But on the x-axis, you might be able to see this. The x component of this vector is about this far, and the x component for these two are just a little bit. So these two x components on these vectors exactly cancel out the x component on this one, cancels out in the x direction. In the y direction, you have an entire vector right here on the y-axis, but the y components on these three bottom ones are a little y component, a little y component, and a little y component. And those three little y components exactly, whoops, cancel out with the giant vector up here. So they're all going to cancel out in the y direction. The final direction is the z direction. Is anything moving towards us or away from us? Well, that's these two. This one's moving towards us a little bit, so there's a little bit of z component coming towards us, but this dotted line bond is going back the exact same amount. So on the z-axis, the z components cancel out. So without actually doing it for you mathematically, these are actually perfectly symmetrical. They all cancel out. So if you at least just understand that, 2 dipole moments that are linear, 3 dipole moments that are trigonal planar, or 4 dipole moments that are tetrahedral are perfectly symmetrical, if you ever draw any one of those 3 sets in a molecule, you can erase them because they cancel out. And then we're going to look at our molecule, and actually after we've erased anything that's symmetrical, if there are dipole moments left over, it's a polar molecule, and if there aren't any left over, it's nonpolar. Let's give it a try. Here's a carbon dioxide molecule. This is its correct Lewis structure. If you want to predict whether it's a polar molecule or a nonpolar molecule, you have to determine the shape and then draw its correct shape. What's the steric number of the carbon in this molecule?
2.
Correct. It's not how many bonds there are, it's how many bonded atoms there are. So 2 bonded atoms, steric number is 2. 2 groups spread themselves out as far apart as possible, like this. Now, if I were to ask you to try to figure out if this is polar or not, Ms. Eckes, this might be one of the examples where I might not tell you the electronegativities of carbon and oxygen, because you can tell what they are relative to each other by looking at the periodic table. If you look at carbon and oxygen's positions on the periodic table, you can tell definitely that one of those has to have a higher electronegativity than the other. Which one has to be higher?
Oxygen.
because it's closer to the upper right-hand corner. That's the general trend. So without even looking up anything on handout 8, I would go, well, oxygen's got to be higher than carbon. So these are going to be polar bonds. And so I'm going to draw my little dipole moment arrows from the C to the O. Does that make sense? Okay. If I gave you 2 where it was ambiguous and you couldn't tell from their positions on the periodic table, that's when I would for sure give you their electronegativities. But something like this, all you really need to know is, are they the same or are they different? And because they're in the same row and oxygen's further to the right, it's got to be higher. So once you've drawn all the dipole moment arrows along every bond in the molecule, then you ask yourself, okay, are there any symmetrical sets? Is there 4 dipole moments in a tetrahedron? No. Are there 3 dipole moments trigonal planar? No. Are there 2 dipole moments that are linear? Yes. So that means erase them. And now you're done. Now you look at the molecule. If you have dipole moments left over, it's a polar molecule. But if you don't have any dipole moments left over, that means the electrons are staying perfectly evenly symmetrically arranged around all the atoms, and we would call that a non-polar molecule. Okay. So with no remaining dipole moments, we conclude the CO2 molecule is nonpolar. Okay. Let's go back and look at some of the molecules we did with our other technique at the beginning of the period. Let's go back to water. So the water molecule had a Lewis structure like this. We determined it had a bent shape, so let me draw it as this bent shape. I may not necessarily tell you what the electronegativities are for these 2 elements, because you should be able to tell oxygens should be quite higher than hydrogens. So these would be polar bonds. So you can draw the dipole moment arrows along each of the bonds, pointing from the hydrogen to the oxygen. And both bonds would be identical, so I draw these 2 dipole moments exactly the same. Once you've put dipole moments on every single bond, then you ask the question, are there any symmetrical dipole moments? Are there 4 dipole moments that are tetrahedral? No. Are there 3 dipole moments that are trigonal planar? No. Are there 2 dipole moments that are linear?
No.
No, good, that's not a line. So you passed geometry, excellent, thank you very much. So these are not linear, they don't cancel out. I've done every test I could do, I'm done. Look at the molecule. There's dipole moments left in it. So if you have remaining dipole moments, what does that mean? That means the arrows are showing you where the electrons are being pulled to. They're being pulled to the oxygen. The oxygen's going to be the negative end of the molecule, and the hydrogen's going to be the positive end. So this is a polar molecule. You following that okay? Let's try the next one we did earlier, the ammonia molecule. Lewis structure for ammonia looked like this. Steric number 4 with 1 lone pair means the molecular geometry was trigonal pyramidal. So we have to draw a good trigonal pyramidal shape so you can actually see the 3 hydrogens are the base of a pyramid, and they're all coming up to the nitrogen at the top of the pyramid. Once again, I would not necessarily for this problem tell you the electronegativities of the 2 elements, because nitrogen's so far over onto the right side of the periodic table, it has to have a higher electronegativity than hydrogen. So these bonds would be polar. So I'm going to draw my dipole moment arrows along the bonds pointing from the hydrogen to the nitrogen. Okay. Once you've done that, then you go, okay, are there any symmetrical arrangements of dipole moments? Are there 4 dipole moments in a tetrahedron? No. Are there 3 dipole moments that are trigonal planar? No, you're shaking your head no?
No.
How come?
Oh, wait, never mind.
I see 3 of them.
Yeah, I got it.
Because that's a plane, right?
Mm-hmm.
Plane. What did you learn in geometry in high school? A plane is something that is flat, right? Like the Great Plains. Is that a flat molecule?
No, it's not.
Wait a second. If that's not flat, then it can't be a plane. This isn't trigonal planar. This is trigonal pyramidal. It's a pyramid. This is not trigonal planar. Mr. DiFilippo, you had the answer right at first, and I tricked you into changing it. This is not a plane. This is a pyramid. So those 3 dipole moments do not cancel out because they're not flat. So you can't cancel them out because they're not trigonal planar, and there certainly aren't 2 dipole moments that are linear. So we're done. I can't erase anything. I have remaining dipole moments. And where are these dipole moments pointing? You see they're all pointing slightly upward. It's the top of the pyramid that's in negative where the electrons are going, and the bottom of the pyramid where the hydrogens are that they're leaving. That's the positive end on the bottom, the negative end on the top. So this is a polar molecule. But now Mr. DiFilippo will never miss the difference between a pyramid and a plane anymore now, right? Good. Hopefully nobody else also, right? So this has to be polar for that reason. Does that make sense? Okay, lovely, okay. The next one we had done with the original technique was carbon tetrafluoride. We knew that the central atom had a steric number of 4, so it's going to make a tetrahedrally shaped molecule. So you have to do your best job to draw that tetrahedral molecule. So just once again, you draw one bond pointing directly up, flat on the paper. When you draw that straight line, it means it's on the paper. Another one has to be coming down to the right at an angle equal to 109.5. And if you don't have a protractor, I won't kill you on that. But just don't make that angle look 90 degrees because it isn't 90 degrees. It's a little bit bigger, 109. And then when you have a tetrahedron, you have 2 other fluorines that are not on the plane of the paper. You cannot draw those bonds as straight lines in. If you do, I'm going to mark it wrong because I'm going to think you're drawing me a planar flat molecule. If you mean this fluorine is to be in front of the plane of the paper, draw a wedge. If you mean this fluorine is to be behind the carbon, behind the plane of the paper, draw a dotted line. That's how you make your representation look 3-dimensional. Fluorine has a higher electronegativity, so these bonds are all polar. So I would draw my dipole moment arrows along each of the bonds. And then once you've labeled every single bond, you ask these 3 relevant questions again. Are there 2 dipole moments that are linear? No. Are there 3 dipole moments that are trigonal planar? No. Are there 4 equal magnitude dipole moments that are tetrahedral? What's that shape called? This molecule's shape is called?
Trigonal Bipyramidal?
No, that's with a group of 5. That is a pyramid up and a pyramid down. This actually is a tetrahedron. It's a 4-sided figure with 4 equilateral triangles and it has 4 corners. So this actually is 4 dipole moments arranged in a tetrahedron. So therefore this is a symmetrical arrangement of dipole moments. So you erase them all. And when you're done, there's none left over. So with no remaining dipole moments, that means that this molecule must be nonpolar. Okay. So this is how you predict polarity with dipole moments. And you may be asking yourself, if I'm getting the same answers for this dipole moment method as I did with my simple geometry method with the pluses and minuses and the lines, why am I even wasting my time learning this? Because there's some molecules where the previous technique does not work, and let me show you one that it doesn't. If you draw the Lewis structure for this is a type of compound called a chlorofluorocarbon. It's a refrigerant type molecule. We'll talk about it later in the semester when we deal with atmospheric chemistry. But this molecule has a Lewis structure as shown. All the atoms have octets. The shape should be easy to determine. The carbon has a steric number of 4. And when you have 4 repelling groups, those 4 repelling groups spread themselves out not as a trigonal bipyramidal shape, but as a tetrahedral shape. So this is a tetrahedron I'm drawing here, okay? Now, for each of these bonds, carbon has the lowest electronegativity, fluorine and chlorine are higher. So if we would use our original technique to do that and put positives and negatives, I'd put a negative, positive, negative, positive, negative, positive, negative, positive. And you look at that and go, all the negatives are on the outside, the positives on the inside. I can't draw a line. You would say nonpolar. And you'd be wrong. Because if we take this molecular sample of this liquid substance, if we put it in a device called a polarimeter, it's going to tell, well, that's actually not a polarimeter, but if we put in something that measures dipole moments, we're going to learn that that molecule is polar. And that first technique would have come out wrong. Let's apply the dipole moment technique, okay? If I draw the dipole moment arrows for the carbon-fluorine bonds, whose length represents the difference in electronegativity between carbon and fluorine, which is the difference 4.0 to 2.5, that difference is 1.5. I'll draw those 3 dipole moments like that. Carbon's and chlorine's electronegativities, carbon is 2.5, chlorine is 3.0. What's the difference between 3.0 and 2.5?
0.5.
Only 0.5, which is less than the 1.5 for the other 3. So how should I draw the dipole moment arrow for the chlorine?
A lot smaller.
That's the ticket, because it should be correspond to a difference of 0.5, where the yellow dipole moment arrows are corresponding to a difference of 1.5. Excellent. Now, if you ask your questions, are there 2 dipole moments that are linear, that are equal magnitude? No. Are there 3 dipole moments that are trigonal planar? No. Are there 4 equal magnitude dipole moments that are tetrahedral? They're tetrahedral, but they're not equal magnitude. That means they don't cancel out. So there's no symmetrical dipole moments here because the carbon-chlorine dipole moment is smaller than the carbon-fluorine. The symmetry rules we learned have to be when all the dipole moments are the same magnitude. And if you have one little bond that's different from the others, they are not symmetrical. So we therefore cannot cancel these out. And if you cannot cancel them out, you don't erase them. So this means the molecule turns out to be polar. This is less intuitively obvious, but can you look at the molecule and tell me which half or what part of the molecule is going to be the negative half?
The lower part?
Which one?
The lower part?
Yeah, because the bigger dipole moments are pointing down towards the fluorine. You have such a small dipole moment pointing up that the 3 yellow ones pull the electrons down to the bottom. So the fluorine half will be negative and the chlorine half will wind up being positive.